Okay, so yesterday we talked about the ionization of water, which basically is the back and forth of the the molecules between hydrogen and hydroxide. But the reason it stays neutral is because for every water molecule that goes back and forth, there's one hydrogen and one hydroxide. So that keeps it neutral. We talked about how the Kw is the hydrogen concentration of the hydrogen and times the concentration of the hydroxide. It is equal to 1.0 times 10 to the minus 14 at 25 degrees. And if that temperature changes, then that Kw changes. These two are equal because of this dissociation. And so therefore, each one of these is equal to the square root of the Kw, x, right, square root, which is, because x squared, which is 1.0 times 10 to the minus 7. Now, if the solution, any solution, an acid, is basic, then the concentration of the hydroxide is greater than 1.0 times 10 to the negative 7. If the concentration is acidic, then the concentration of the H plus is greater. And if this occurs, what I didn't say yesterday, is because these two equal 1.0 times 10 to the minus 14. If the concentration of the hydroxide is greater than 1.0 times 10 to the negative 7, then the hydrogen is less. They're not equal. So this is an indirect proportion, right? As one goes up, the other goes down. All right? So if the hydrogen is greater than, then the hydroxide is less than. If the solution is neutral, then they are equal. Now, the next stage in this is talking about all the formulas for pH. So you're going to want to make, like, this is going to be a section, right? A section where we talk about pH. The pH scale is from 0 to 14, acid to base, with 7 being neutral. Now, important in here is pH sig figs. They're weird. I don't know why they're like this. The pH decimal places equal the significant figures in the concentration of the H plus. Yep, totally weird. So if we go back up here and your significant figures is 1.0, that means that your pH is going to be like 4.23 with 2 decimal places, because your significant figures in this was 1.0. All right, your decimal points, it's very strange, I don't understand why, but that's the way it is. The decimal points in your pH equal the significant figures in the concentration of the H plus. Now, if your pH is less than 7, it is acidic. If your pH is greater than 7, it's basic. And if your pH equals 7, it's neutral. All right, so here come the formulas, all right? pH is equal to negative log of the concentration of H plus. pOH is equal to negative log of the concentration of OH minus. pH plus POH equals 14. The concentration of H plus equals 10 to the minus pH. That's important, by the way. The concentration of the OH minus is equal to 10 to the minus POH. Now, if you're given the pH of a solution and asked to find the concentration of the hydroxide, and you have the pH, you can subtract the pH from 14, get the POH, and then take 10 to the minus POH. See that? So it's kind of nice because you can find all of these things by manipulating all these variables. All right? Now, there's also something called the pKa, which is equal to the negative log of the Ka. There's also the pKb, but we're not going to get into that quite yet. All right? The smaller the pKa, and this is important because it's a quick reference, quick ref, like on the AP exam. You can quickly take the log of the Ka and two of them and compare them, because the smaller the pKa, the stronger the acid. And there it is. See? The stronger the acid. So that's what I was saying, Nico. Like, I can run a quick number on that, right? So for example, if you have a Ka, example, equal to 1.1 times 10 to the minus 2, you're going to have a pKa equal to 1.96. If you have a Ka equal to 1.8 times 10 to the minus 4. Now, first of all, this is Ka1 and this is Ka2. Ka1 is indicating a stronger acid. Because it is a higher Ka, it is indicating a greater dissociation to hydrogen and whatever, the base, the conjugate base, right? So it's moving more toward products because the Ka is higher, right? So the pKa here is equal to 3.74. The smaller the pKa, the stronger the acid. So the higher the Ka, right, the smaller the pKa, the stronger the acid. Now, what's the difference? Well, you're going to find out when we do titrations that the Ka is at this inflection point, that the pKa is at this inflection point, that the pKa shows up naturally in some places, and you can just look at a graph and see it, kind of thing. So you go, oh, this pKa is here and this pKa is here, and you know. All right, so these are important things to know, all right, because you can quickly do a reference check on them. All right. So now, what we want to do is we want to be able to find the pH of strong acids and the pH of weak acids. So let's start with finding the pH of strong acids. Super easy because they dissociate 100%. %100% dissociation. So if I take HCl, for example, hydrochloric acid, which is aqueous, and I'm going to dissociate it to H plus Cl minus. Okay, so we're going to start with 0.010 molarity. And what's going to happen is there's going to be this dissociation, thank you, to 0.010 molarity. Why? Because there's going to be 100% dissociation, right? 100%. So the pH is going to be equal to negative log of 0.010. And that's going to be equal to 2 significant digits, 0, 0. Super easy. The reason is it's getting 100% dissociation on that the strong acid. So this is one of the things. Strong acid. So this is one of the reasons that knowing what is a strong acid and what is a weak acid is super important on that exam. Because this could take 2 seconds, but if you decided to do an ice table on it, you know, it's 5 minutes that you don't need to take, right? Okay? All right, so what about weak acids? So you're going to use an ice table. To determine the concentration of the H+. So, for example, we're going to use HCN, which is a super common weak acid to use. You'll see it a lot. It has a Ka of 4.9 times 10 to the minus 10. Look how small that is, all right? So first of all, we know our 5% rule is going to work, right? So when you see something this small, if it's on the test, you know you can assume the 5% rule. So assume it, mark it, and test it, all right? And write that. Assume 5% rule, cross out your X. Use that, then when you get an answer, mark it and test it. Show that testing the 5% rule, okay? So it's at 25 degrees Celsius, and your initial concentration is equal to 0.100 molarity. So I'm going to set up my ice table. Now I'm going to use my Ka. So I'm going to say 4.9 times 10 to the minus 10th is equal to my x squared here, right, because of these two for my products, over 0.100 minus x. I'm going to assume 5%, which gives me, so I can cross this out. That's a nice way to do it, putting a circle around it and running through it. Then I'm going to solve, and I can just say x is equal to 7 0.0 times 10 to the minus 6. Now I'm going to test 7.0 times 10 to the minus 6 divided by 0.100 times 100, and I get 0.007%. I don't have anything to worry about. So pass. So good, right? Next, I'm just going to say my H plus concentration is equal to 7.0 times 10 to the minus 6. So my pH is equal to negative log 7.0 times 10 to the minus 6. So my pH is equal to 5.15. Zero. 3 digits. So there should be a 0 in there, I think. Something, whatever the next number is. There should be 3 digits because of the initial concentration had 3 digits in it. So my sig fig should be 3 somewhere. 3 digits. I don't know why there's only 2. All right? Questions? Significant figures on the AP exam traditionally have been plus or minus 1. So generally teachers just say, like, if in doubt, just put 2. Because either going to be 1 or it's going to be 3. Put 2. You're going to be okay, right? All right, questions? All right, we're going to be in this unit for a while. I mean, not like a long time, but like this is a thing. Because the next chapter is acids and bases also. It's buffers. Like it's more acids and bases. We're going to do a titration. So we have 3 chapters left. This is a big one. The next one is more of what we've already done, and then batteries. Batteries is a huge one. We got to be in batteries for a while. There's always a battery question. And then we're done. So we're down to the wire, but this is important. The next one we do is, the next big one that we do is solubility, which is basically this, but if you have sodium chloride and you get sodium and chloride, we don't use the sodium chloride because it's a solid. So it's the exact same thing that we're doing here. It's just that it's sodium and chloride. And there's a Q for it. So that's basically it. So we're like gonna move straight through and we're gonna finish this up. We're gonna finish, and then we gotta get to batteries. That's where we're done. That's when we're done. Batteries is our last unit. All right, so homework, I'm just about finished posting. Like I just got to pick out the last problems. That's why I'm stopping now, okay? Okay. And tomorrow I'll get you that list, which will be super helpful, and I'm putting together the study list, which you'll get at the beginning of April. So that's going to be 772 if you want to take a picture.